Alright, we have some standard surfaces then in R3 that we'd like to look at. These are called quadric surfaces. And you can kind of think about these as being related to the conic sections in R2. The conic sections, of course, being things we can get when we slice the cone in certain ways, like hyperbola, parabola, ellipse, things of that nature. So let's go ahead and take a look at some of these things. Let's start with the ellipsoid. Okay, this is going to be an equation, a three-variable equation of this form: x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. All right. And the way you can think about this is looking at the conic sections on your xy, xz, and yz coordinate planes respectively. So in other words, if I look, say, on the xy plane, and actually let's look at a specific example, shall we? Let's say I want to have x squared over 4 plus y squared over 9 plus z squared equals 1. If you like, you can think about that as z squared over 1 squared. Okay, so let's look on the xy plane. On the xy plane, z is equal to 0. I just have x squared over 4 plus y squared over 9 equals 1. Now, I know a lot of you did not spend a lot of time on conic sections in high school or algebra class, but quick reminder of what those look like. This is going to be an ellipse that intersects the y-axis at plus or minus 3. Let's try that again. And the x-axis at plus or minus 2. So there you have it. Okay. Now let's think about the, let's go to the xz plane. So on the xz plane, we just have the equation y is equal to 0 here, x squared over 4 plus z squared is equal to 1. So sketching the graph of that, on the xz plane, we're going to be intercepting the z-axis at plus or minus 1, the x-axis at plus or minus 2. And then one more here, let's look at the yz plane. When x is equal to 0, you'd have y squared over 9 plus z squared equals 1. So I think you might have the idea of these ellipses now. Don't know why they're not taught more often. They're really not that bad. Here's y, we'll say, here's z, intercepting the y-axis at plus or minus 3, the z-axis at plus or minus 1. Now, putting these all together in a nice three-dimensional picture is a bit on the tricky side, but I'm going to give it my best shot for you. So we have, here's x, y, and z. We're intercepting the x-axis at plus or minus 2, intercepting the y-axis at plus or minus 3, and the z-axis at plus or minus 1. So if we put all these things together, let's see, maybe I can draw them with the appropriate colors as well. Here is our ellipse on the xy plane. Here is our ellipse on the xz plane. And here is our ellipse on the yz plane. Okay, and if you put them all together, you get this ellipsoid, and so you sort of have something like this. I'm trying to give it a little bit of, what's the word? Gravitas? Is that the word? A little bit of substance, I guess. Much better pictures in the book, of course, but you have this ellipsoid here that any cross section of it is going to be an ellipse, and we can see that by looking at the xy, yz, and xz plane. So there's a general idea. Let's take a look at a couple more of these quadric sections. Next one I want to look at is the cone, the general form: x squared over a squared plus y squared over b squared equals z squared over c squared. So again, let's look at a specific example. Let's take x squared over 4 plus y squared over 9 equals z squared over 1 again. Okay, just to get the idea. Since the z squared's on the right, the cone is going to be opening up left and right. And what you're going to have, if you fix different values of z squared, you're going to have different ellipses here. So, for example, if I look on the xy, let's try that different color, xy plane, where z is equal to 0, there's only one thing that's going to work here. that is the origin 0, 0. So let's start putting our sketch together here. On the xy plane itself, there's only one point in this surface. That's the origin right here at 0, 0. Now if I take different values of z, for example, if I take z to be equal to, well, either plus or minus 1, what do I have? I have x squared over 4 plus y squared over 9 equals, plus or minus 1 squared is 1, and from what we just did on the previous page, we know that's an ellipse intersecting the x-axis at 2, the y-axis at 3. So it looks like this. And that occurs, again, at the plane where z is equal to 1 or the plane where z is equal to negative 1. So I have this ellipse here and this ellipse here. And I can keep doing that on out, and what I'm going to get are these ellipses that get bigger and bigger like so and form this cone. Okay? If you were to switch some of the variables here, make x squared plus z squared equals y squared, you have a cone opening up on the y-axis. If you have y squared plus z squared equals x squared, you'd have a cone opening up on the x-axis. So again, more on that in your book, and that's what you should really be looking at, as you have already, I know. A couple more of these. Let's talk about the elliptic paraboloid. Elliptic paraboloid here, we have z over a number is equal to x squared over a squared plus y squared over b squared. Here's a specific example. Let's say z is equal to x squared over 4, and let's just say plus y squared. So again, we can look at different points for z. Obviously, if we're on the xy plane where z is equal to 0, we have that same situation as before, that the only way this is going to be true is if xy is equal to 0, 0. So let's start sketching our graph here. There's that point. Now for different heights of z, we're going to get different things. So for example, if I let z be equal to 1, I have x squared over 4 plus y squared equals 1. There's another ellipse. This time it intercepts the x-axis at plus or minus 2, the y-axis at plus or minus 1. So I have an ellipse that looks like this. That's going to be true only when z is equal to 1. Notice there's no solutions for negative z. So at z equals 1, I have this ellipse here that, let's see, would look like a little bit longer on the x, like so. And if I keep doing that for different values of z, I'm going to have this elliptic paraboloid going to be coming out. Well, that stinks. Let me try that again. Let me just back up, back up. Back up, back up. Yeah, let's get rid of this. I'm going to cheat a little bit of my ellipse just to make it look a little bit nicer. I'll have that same ellipse right here, and then we'll have this elliptic paraboloid for different heights of z that looks something like that. The cross sections of these are ellipses. Okay? Now, of course, different things. If we put the x over here to the first power, z squared, and y squared on the other side, we're going to have a paraboloid opening up on the x-axis. And of course, if the y is to the first power, x squared and z squared, we're going to have one opening up on the y-axis. Again, check your book for those different possibilities. Okay, a couple more to go here. One is the hyperboloid. Two types of hyperboloids here. The first one is the old one-sheeter. Hyperboloid of one sheet. That's something of this form. X squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Now again, let's use specific numbers here. I'll just use the same numbers I've been using. Okay, and let's look at the cross sections on the different planes. Let's start with the xy plane. We should get a good idea of what this thing looks like. Here I have x squared over 4 plus y squared over 9 is equal to 1. You are all saying to yourself, hey, I know what that is. That's an ellipse on the xy plane. Intercepts the x-axis at plus or minus 2, y-axis at plus or minus 3. Looks like that. So there's the cross section on the xy plane. It's that ellipse. How about the xz plane? let's see. So y is equal to 0 here. I've got x squared over 4 minus z squared is equal to 1. This is a hyperbola. Again, you may not remember exactly how to sketch a hyperbola here on the xz plane. We're going to intercept the x-axis at plus or minus 2. And this plus or minus 1, what that does for us is it actually gives us a little box here that sort of helps us with our asymptotes. The x squared is positive, so it's going to open up on the x-axis like so. And what that box does for us, by making it intercept at plus or minus 1 on the z, plus or minus 2 on the x, gives us these asymptotes that those hyperbolas parts are going to start hugging. Okay? So there's that, and then we'll have another hyperbola on the yz plane. Let's take a look at that. Here we'd have y squared over 9 minus z squared over 1 is equal to 1. So this is going to intercept, here's y, there's z. The y-axis at plus or minus 3, those are going to be the major vertices. We can make a box here. Let me make it a little bit darker so we can see it. And I can draw the diagonals of this box. It wasn't very clear before. Make that box intercepts the z-axis at plus or minus 1, since 1 squared is underneath z squared. Plus or minus 3, since 3 squared is underneath y squared. These asymptotes are what the hyperbola hugs as it goes off to infinity. So I have these vertices here because the y is the positive term. So the vertices are on the y-axis. And it's going to hug that, and it's going to hug that. It's going to hug this, and it's going to hug this. So there's my hyperbola. Now putting this all together is, again, a little bit tricky. Pictures in the book are better than anything I can draw here. But I think we're going to have a general idea of what this looks like. It's going to open up on the z-axis because the z is the negative. And it's going to just basically be something like this. I'll try and draw these cross sections in. If I cut it on the xy plane, there's my ellipse that I drew before. If I cut it on the xz plane, here's my hyperbola coming down like this, and then the back side of it. That's on the xz plane. If I cut it on the yz plane, I have another hyperbola. I know it looks a little bit different, but here is cutting through the y-axis, and here's the back side of that in that purple there. So you can see how that forms that hyperboloid of one sheet. Alright, last conic section, I do believe, anyway. That's the old two-sheeter. Hyperboloid of two sheets. Here we're going to have two of our terms be negative. Let's just go ahead and look right at the example. X squared over 4 minus y squared over 9 minus z squared over 1 is equal to 1. Now let's take a look at our different planes here. Let's start with the xy plane. Here z is equal to 0, so I have x squared over 4 minus y squared over 9 is equal to 1. Okay, we're recognizing this now as a hyperbola. Make this a little bit nicer. That's going to, let's see, have a box that intercepts at plus or minus 2 on the x, plus or minus 3 on the y. Let me draw my box in here. Alright, let me just change this a little bit. I want some uniformity. I'm not trying to make it a perfect graph, but, you know, doing the best I can. Here's our diagonals. Diagonal, diagonal. These are the asymptotes that our hyperbola is going to fall. X squared is the positive one, so it's going to be vertices on that x-axis hugging those asymptotes as it goes off to infinity. Okay, there's one hyperbola. That's the cross-section of this thing on the xy plane. How about the xz plane? Well, I'm glad you asked. Here, y is equal to 0, so I have x squared over 4 minus z squared is equal to 1, or z squared over 1 if you like. So another hyperbola. Plus or minus 2 on the x, plus or minus 1 on the z is where a box is going to intersect. Draw those diagonals. Diagonals. And let's see, x is the positive, so those are where our vertices are going to be. Opening up on that x-axis, hugging those diagonals as asymptotes. little smoother. There's not a sharp turn. It's a nice smooth turn on these hyperbolas. But when you got a guy drawing them who's not all that smooth, just ask my wife. Yeah, it's a little tough sometimes. Do the best I can. How about the YZ plane? This one's kind of interesting. When x is equal to 0, you have a negative y squared over 9 minus z squared over 1 is equal to 1. So let's see. Let's think about that. Here's my YZ plane. What are all the ordered pairs y comma z that make negative y squared over 9 minus z squared over 1 equal to 1? Yeah, that's it. I've drawn them all right there. No solutions to this. There are no points on the YZ plane as a part of this graph, because you'd have a negative and a negative trying to be equal to a positive. That don't work, does it? So here's our two-sheet hyperboloid then. I'm going to do the best I can drawing it on our x, y, z plane. The x is the positive. That's where my two sheets are going to be. I got action going on at plus or minus 2 on the x-axis. Okay, and here's what it's going to look like. Let me draw it first, and then I'll try and draw in. Okay, I've got this here, and this is not the easiest thing to do. Alright, so basically you got a couple of half balls or something like that kind of opening up in opposite directions. Hyperboloid of two sheets. Again, I know you've seen it in your books, you have a better idea of what's going on. I'll try and draw these hyperbolas here on the xy plane. There's this light blue one. We have this hyperbola here and here. On the xz plane, we have this hyperbola that's coming down like so and like so. And nothing on the yz plane. That's the screen if you think about the x-axis coming out of the screen. So nothing going on there. All right. Oh, shoot, I lied. There is just one more we got to do. One more we're going to look at real quick, and that's the hyperbolic paraboloid. So let me go back here real quick. Of course, you can change this. If your y squared is your positive term, it's going to open up and out on the y-axis. If your z squared is your positive term, it's going to open up and down on the z-axis. All right, now we're back to hyperbolic paraboloid. This would be something of the form z over c equals, let's start with this way, y squared over b squared minus x squared over a squared. So let's say z is equal to y squared over 9 minus x squared over 4. Okay, let's take a look first at let's just look at the yz plane here when x is equal to 0. And so I have z equals y squared over 4. Now what is that going to be? I'm just going to draw these in 3 dimensions as I go, I think. Again, you can see the picture in your book. We're just trying to justify where those pictures come from. That's just on the yz plane. It's just a parabola opening up. So it's just going to be something like this. Okay. Now let's take a look at the xz plane. Here I have z equals negative x squared over 4. That's a parabola, but opening down. So that looks something like this. Now if I add in different y values here, what I'm going to get is parabolas opening down, but they're going to be raised up. And you see we have this sort of saddle-like thing. And similarly, if I change my x value, fix that, then I'm going to have parabolas opening up parallel to the yz plane, but just at different x values. So this gives you a sort of saddle. If you switch the x and the y, you're going to have a saddle that's sort of coming up on the x-axis here. Again, the pictures in your book are much better. Make sure you look at those. But you get the idea, I think. It's a little bit of justification where the hyperbolic paraboloid comes from. All right, you should be in decent shape, I think, to get through that 9.6 homework. All you need now is the password. The password is... Well, it's another very useful one today. Nidiphugus. And that, of course, is just an adjective describing something that will be leaving the nest soon after hatching. Nidiphugus. So I'm sure you'll have occasion to use that word throughout the summer season. Good luck on 9.6. or any season that you're in. Anytime there's birds hatching. Good luck in 9.6. Let me know if you have any questions.